Welcome students to the fifth and final lecture on infinite series. In the last lecture, we have developed the concept of Euler number. As you know, it is denoted by E, and we have discussed that it can be obtained as the limit n going to infinity 1 plus 1 upon n whole to the power n. Let me do this once again to show how it converges to an infinite series whose summation will lead to the Euler constant E. So, consider one plus 1 over n whole to the power n. The kth term for k less than n less than equal to n can be obtained from binomial theorem the kth term for k is equal to 0, 1, 2 up to n is n c k 1 by n whole to the power k. This is equal to factorial n upon factorial k to factorial n minus k into 1 upon n to the power k, which is equal to, after cancelling with this, we get n into n minus 1 up to n minus k minus 1 divided by factorial k to 1 upon n to the power k. Now, let us divide each one of the k terms by 1 n. So, what we are getting? This is equal to 1 minus 1 upon n into 1 minus 2 upon n 1 minus k minus 1 upon n upon factorial k. As n goes to infinity, this whole expression converges to 1 upon factorial k, as each of 1 upon n, 2 upon n and k minus 1 upon n for a fixed k go to 0. Therefore, what we are left with is 1 upon factorial k. Therefore, the limit (1 plus 1 upon n whole to the power n), this converges to, first of all, notice that if n increases and n goes to infinity, then the number of terms that you will find in the series is also going to infinity, and the kth term is going to be 1 upon factorial k. Therefore, the 0th term is 1 upon 0 factorial plus 1 upon 1 factorial plus 1 upon kth term is 1 upon k factorial. Therefore, as n increases, the kth term converges to 1 upon factorial k. Therefore, the infinite series can be seen as it is the sum of 1 upon 0 factorial. So, that is 1 plus 1 upon 1 factorial, that is 1 plus 1 upon 2 factorial plus 1 upon 3 factorial plus this is called Euler's number. Question is, what is the value of it? This is an irrational number. Therefore, we cannot write E as the ratio of two integers, but we can find the limit of it, which is 2.7182818459045 230,365. So, I remember up to this position. For all practical purpose, we typically use up to 3 or 4 decimal places, and people have tried to compute its value through computers. But since computers also have a limit of the number of decimal places, for all practical purposes, we have to take an approximation to that one, and therefore, using a third or fourth decimal places after the decimal point is good enough for our practical purpose. Now, it is very easy to find out that this number has to be greater than 2 because of the first two terms. This is 2 and the remaining sum, it is an infinite sum, but all the terms of this summation are positive real numbers, in fact positive rational numbers. It is 1 upon some k factorial. Therefore, it is easy to see that this part is going to be positive, it cannot be negative. Therefore, E has to be greater than 2, that is very clear. How do we know that it is not greater than 3? So, we have to see that the bound on these infinite sum is 1. Let us verify that. So, consider 1 upon factorial 2 plus 1 upon factorial 3 plus 1 upon factorial 4 plus is equal to 1 upon 2 plus 1 upon 2 into 3 plus 1 upon 2 into 3 into 4 plus 1 upon 2 into 3 into 4 into 5, like that. Now, replace all other numbers with 2. So, this is less than 1 upon 2. This quantity is less than 1 upon 2 into 2. because 3 is greater than 2, therefore 1 upon 3 is smaller than 2, plus 1 upon 2 into 2 plus 1 upon 2 to the power 4, like that. Now, this is a GP series of the form half plus half square plus half cube plus half to the power 4, like that, and we can sum this GP series. As n goes to infinity, this converges to half into 1 upon 1 minus half, which is equal to 1. Therefore, we have seen that E is greater than 2, but the part that is remaining above 2 is less than 1. Therefore, we can easily say that 2 is less than E less than 2 plus 1 is equal to 3. Therefore, we know that it is between 2 and 3, and the actual value was that I have shown some time back, 2.7, 1828, 1828, etc. Now, let us consider e to the power x for some real or complex x. Question is, what is going to be the series I am not going to prove, but I am just writing the result that e to the power x is equal to 1 plus x square upon factorial 2 plus x cube upon factorial 3 plus this infinite sum is called e to the power x. Let me give you an intuitive idea how it came. Consider E square. We know that E square is equal to E multiplied by E. Therefore, we can write it as limit n goes to infinity 1 plus 1 upon n whole to the power 2n is equal to limit n goes to infinity 1 plus 1 by n whole square whole to the power n is equal to limit n goes to infinity 1 plus 2 by n plus 1 by n square whole to the power n. So, the kth term for 0 less than equal to k less than equal to n is n c k 2 by n plus 1 by n square whole to the power k is equal to factorial n factorial k factorial n minus k 1 upon n whole to the power k into 2 plus 1 upon n whole to the power k is equal to, by using the same trick that we did some time back with respect to E, this is becoming 1 into 1 minus 1 upon n up to 1 minus k minus 1 upon n upon factorial k 2 plus 1 upon n whole to the power k. Therefore, when we take limit for a fixed k, this limit becomes 1 upon factorial k 2 to the power k. Therefore, E square is actually the summation whose kth term is 2 to the power k upon factorial k. Therefore, it is 0th term 2 to the power 0 upon factorial 0 plus 2 to the power 1 upon factorial 1 plus 2 to the power k upon factorial k, or we get the series like this: 1 plus 2 upon factorial 1 plus 2 square upon factorial 2 to the power k upon factorial k. This is not a proof, but this shows how E square can be written as an infinite series involving 1 plus 2 upon factorial 1 plus 2 square upon factorial 2, etc., up to infinity. So, this gives an idea that e to the power x is 1 plus x square upon factorial 2, x cube upon factorial 3, etc., up to infinity. Therefore, what is e to the power minus x? By replacing x with minus x, we can easily get that it is 1 minus x plus x square upon factorial 2 minus x cube upon factorial 3 plus this infinite sum, where alternate terms will come out to be positive and negative. Let us now consider a complex number purely imaginary e to the power I x. All of you know about I is the root over minus 1, and we use it for denoting complex numbers. In fact, a plus ib all of you are very familiar with. By expanding in the similar way, we get this is 1 plus I x plus I x square upon factorial 2 plus I x cube upon factorial 3 plus I x to the power 4 upon factorial 4 plus I x to the power 5 upon factorial 5 plus I x to the power 6 upon factorial 6, etc. we know I square is equal to minus 1. Therefore, this can be written as 1 plus I x, I square is equal to minus 1. So, minus x square upon factorial 2. So, I cube is equal to minus I x cube upon factorial 3, I to the power 4 is equal to 1. Therefore, it is x 4 upon factorial 4 plus I x to the power 5 upon factorial 5, etc. Let us now separate out the real terms and imaginary terms. So, what we get is 1 minus x square by factorial 2 plus x to the power 4 upon factorial 4 minus x to the power 6 upon factorial 6, etc., plus I times x minus x cube upon factorial 3 plus x to the power 5 upon factorial 5, etc. Now, do you recognize these two series separately? Do you? About 2 classes back, we have discussed that this is nothing but cos x and this is sin x. Therefore, what we can see that e to the power I x can actually be written as cos x plus I sin x. Okay. Let us move further. Let me solve an example. Find the value of one upon factorial 1 plus 2 upon factorial 2 plus 3 upon factorial 3, etc. What it is going to be? We can see that it is not exactly what is written for E, because for E it is 1 upon factorial 2, 1 upon factorial 3, etc. But what we can do? We can write it as 1 upon 1 factorial plus 1 upon 1 factorial. We can cancel the 2 plus 3 cancels with 3 is equal to 1 upon 2 factorial plus 1 upon 3 factorial plus like that. Therefore, we can see that this is also equal to E. What about the next problem? If we have x upon 1 factorial plus 2x upon 2 factorial plus 3x upon 3 factorial up to infinity, we can easily see that it is x taken out, it is 1 upon 1 factorial plus 2 upon 2 factorial plus 3 upon 3 factorial is equal to x times E. Let me do a slightly different problem. What is n is equal to 0 to infinity 1 upon n minus 1 factorial. We know that at n is equal to 0, the denominator is equal to minus 1 factorial. and minus 1 factorial does not have any meaning. Therefore, we can write it as n is equal to 1 to infinity 1 upon n minus 1 factorial, and we can easily see now that this is equal to sigma, say m is equal to 0 to infinity 1 upon m factorial, where m is equal to n minus 1. Therefore, if we are summing 1 upon n minus 1 factorial from n is equal to 1 to infinity, we get that is also is equal to E. If we move further and suppose we want to find out what is sigma 1 upon n minus 2 factorial, n is equal to 0 to infinity. If that is the problem, then as before, this is actually equal to n is equal to 2 to infinity 1 upon n minus 2 factorial, which is at n is equal to 2, it is 1 upon 0 factorial. At n is equal to 3, this gives us 1 upon 1 factorial. At n is equal to 4, it is 1 upon 2 factorial, like that. Therefore, that is also is equal to E. Therefore, we can find an expression that is apparently different from the standard expansion of E, but we can make some algebraic manipulation to convert it into E or some of its function. For example, what is sigma I square upon factorial I is equal to 0 to infinity. This is equal to, as you can easily see that I is equal to 0, it is 0. This is we can write I is equal to 1 to infinity I square upon I factorial. So, what is the kth term? K square upon factorial k, which is k upon k minus 1 factorial, which is equal to k minus 1 plus 1 upon k minus 1 factorial, which is equal to k minus 1 upon k minus 1 factorial plus 1 upon k minus 1 factorial, which is equal to 1 upon k minus 2 factorial plus 1 upon k minus 1 factorial. Now, just now we have seen that this, when we sum for k is equal to 2 to infinity, is going to be E, and this when we sum from 1 to infinity, this is going to be E. Therefore, the whole sum is going to be E plus E is equal to twice E. Therefore, we can see that summation of I square upon I factorial is equal to twice E. Slightly more harder problem. Find the value of sigma n cube upon n factorial n is equal to 1 to n is equal to 0 to infinity. So, this we can write it as summation n is equal to 1 to infinity n square upon n minus 1 factorial, which is equal to sigma n is equal to 1 to infinity n minus 1 whole square, which is n square minus 2n plus 1. So, we need to compensate for that. So, it plus 2n minus 1 divided by n minus 1 factorial. This is equal to sigma n is equal to 1 to infinity n minus 1 whole square divided by n minus 1 factorial. So, 1 n minus 1 cancels. So, it is n minus 1 upon n minus 2 factorial plus 2 times summation n upon n minus 1 factorial minus summation 1 upon n minus 1 factorial n is equal to 1 to infinity. Here again we make the manipulation. So, it is sigma over n minus 2 plus 1 into n minus 2 factorial plus 2 into sigma n minus 1 plus 1 upon n minus 1 factorial minus sigma 1 upon n minus 1 factorial. So, this is going to be sigma 1 upon n minus 3 factorial plus sigma 1 upon n minus 2 factorial plus 2 times sigma n minus 1 cancels with n minus 1. So, n minus 2 factorial plus 2 times sigma 1 upon n minus 1 factorial minus 1 upon n minus 1 factorial. Some time back we have seen that sigma 1 upon n minus 1 factorial, that gives rise to E, sigma 1 upon n minus 2, that also gives rise to E. Therefore, similar way we can find that sigma 1 upon n minus 3 factorial, sigma 1 upon n minus 3 factorial will give an E. So, we find E plus E, this gives us 2E, this gives us 2E minus E. So, what we are left with is E plus E plus 2E plus 2E minus E. E plus E plus 2E plus 2E minus E. So, what is that? This is equal to 5E. So, the summation sigma n cube upon n factorial is equal to 5E. One more problem. Consider 1 upon 1 factorial plus 1 plus 2 upon 2 factorial plus 1 plus 2 plus 3 upon 3 factorial. What is the value of this series? We can see that the kth term is sigma I 1 to k divided by k factorial, which is k into k plus 1 by 2 divided by k factorial, which is equal to half times k upon k factorial plus k plus 1 upon k factorial. Which is equal to half times 1 upon k minus 1 factorial plus 1 upon k minus 1 factorial plus 1 upon k factorial. Therefore, if we take sum, can be written as half sigma 1 upon say k minus 1 factorial plus sigma 1 upon k minus 1 factorial plus sigma 1 upon k factorial. And we have already seen that this converges to E, this converges to E, and this converges to E. Therefore, the whole series converges to three by 2 E. Let us now look at a slightly different problem. Suppose you are asked to find the coefficient of x to the power 4 in 1 plus 2x plus 3x square into e to the power minus x. So, we proceed in the following way. We take the series expansion of 1 e to the power minus x, and that we multiply by the second degree polynomial 1 plus 2x plus 3x square into e to the power minus x is 1 minus x plus x square upon factorial 2 minus x cube upon factorial 3 plus x to the power 4 upon factorial 4, etc. Now, we try to find in how many different ways x to the power 4 can be formed. So, 1 multiplied by x to the power 4, this will give x to the power 4, and the corresponding coefficient is 1 upon factorial 4. This x multiplied by x cube will give rise to x to the power 4, and therefore, the corresponding coefficient is going to be 2 upon factorial 3 to minus 1 upon factorial 3 plus 3 x square into x square upon factorial 2 will give us 3 upon factorial 2. this is equal to 1 upon 24 minus 2 upon 6 plus 3 upon 2. Okay. This is equal to so it is 1 minus 8 plus 36, which is equal to 29 upon 24. Let me do a slightly different problem. Where ln is natural log, ln is equal to log to the base e. So, what is going to be the value of the infinite series which is of this form? We can easily see that it is the e to the power 5 ln 3, right, because the expansion pattern is like e to the power x. So, this is equal to e to the power 5 ln 3, and we know that this is equal to, and e to the power log of 3 to the power 5 is equal to 3 to the power 5. Therefore, this infinite series adds to 3 to the power 5. So, let me do the final problem on this topic. Find the expansion for e to the power x cos x. We already know the expansion of e to the power x. We already know that expansion for cos x, but what is going to be the expansion for e to the power x by cos x? For such problems, we have to go in the following way. Let the corresponding series be C0 plus C1x plus C2x square plus C3x cube, this infinite polynomial, and we need to find out the individual coefficients C0, C1, C2 up to infinity. Therefore, we can see that e to the power x can be written as the product of cos x time this polynomial. So, we have e to the power x is equal to cos x into C0 plus C1x plus C2x square plus C3x cube. Now, e to the power x is equal to 1 plus x square upon factorial 2 plus x cube upon factorial 3, and cos x is equal to 1 minus x square upon factorial 2 plus x to the power 4 upon factorial 4 multiplied by C0 plus C1 x plus C2 x square C3 x cube. So, we can find out the coefficients of individual powers of x from the product of the two polynomials, and then equating it with the corresponding coefficient in the expansion of e to the power x, we can obtain the values of C0, C1, C2, etc. So, let me do for first few powers of x. When it is x to the power 0, we find the coefficient on this side is 1, on this side it is C0 into 1. Therefore, it implies C0 is equal to 1. Now, let us consider x to the power 1. Its coefficient on this side is 1. On this side, the coefficient of x to the power 1 is C1 multiplied by 1, implies that C1 is equal to 1. What is the coefficient of x square? X square, on this side we have 1 upon 2. On this side we can get x square as C2 times 1 minus C0 by 2. What does it imply? It implies that C0 minus half is equal to half, C2 minus half is equal to half. Therefore, C2 is equal to 1. Let me go one more step. For x cube, on this side we have 1 upon factorial 3. On this side we have C3 minus C1 by 2 implies 1 by 6 is equal to C3 minus half. Therefore, C3 is equal to half plus 1 by 6, which is equal to 2 by 3. We are getting that the coefficients e to the power x upon cos x are C0 is equal to 1, C1 is equal to 1, C2 is equal to 1, C3 is equal to 2 by 3. In fact, you can try to find out C4 is equal to half, C5 is equal to 3 by 10, etc. So, by comparing the coefficients of two series, when one is known, we can obtain the coefficients of the other series for which the coefficients are unknown. Okay, students, with that I conclude my lectures on exponential series. Hope I have taken care of varieties of problems, and that will help you solving problems on series expansion. Thank you.